This video looks at the practical steps involved in synthesizing an organic product that's liquid at room temperature. If it's solid at room temperature, then there's some different steps involved, and you'll look at those on another occasion. In this case, the substance we'll be synthesizing is 2-chloro-2-methyl propane. Structure shown there, full structural and skeletal. And to do that, we're going to be using these reactants: concentrated hydrochloric acid and 2-methyl propan-2-ol. The reaction is a substitution reaction. The chlorine from the hydrochloric acid will substitute for the alcohol group in the 2-methyl propan-2-ol, giving the 2-chloro-2-methyl propane and water. First step will be to measure out some of the 2-methyl propan-2-ol reactant, and we're going to measure the mass of the amount we're using so we can work out the percentage yield at the end. You're going to need a 250 centimetre cubed conical flask, and bring it over to the balance where you'll find the alcohol and a 10 cm cubed measuring cylinder. So you're going to use a dropping pipette to transfer approximately 6.5 centimetres cubed of the alcohol into the measuring cylinder. Be careful when you're doing this, as shown. Try not to spill any. Always minimise the amount of chemicals that end up on the bench. Keep the bottle as close as you can to the measuring cylinder. And we're going to be wearing gloves throughout this practical. The alcohol itself is not particularly hazardous, but we will be using concentrated hydrochloric acid, and that's corrosive. So throughout the whole practical, you're going to be wearing a lab coat, safety specs, and gloves. We want to know the mass of the alcohol, so we're going to put the conical flask onto a balance and tare the balance to 0, and then we can tip the alcohol into the flask, and the weight of the flask on the balance will tell us precisely the amount of alcohol that we're using. You'll need to record this mass carefully so that you can work out the percentage yield at the end. The next step is to add the concentrated hydrochloric acid. This will be found in the fume cupboard because of its corrosive nature and the fumes it gives off. You're going to measure out 20 centimetres cubed into a 50 centimetre cubed measuring cylinder, and then this is going to be added in small portions to the conical flask, swirling after each addition. Be cautious when you're doing this. Don't tip it in all at once. There will be an exothermic reaction as you add it, and some acidic fumes get given off, so don't hold this flask close to your face where you might inhale some of those fumes. So just keep adding portion after portion, swirling between each one. You don't need to be too conservative, so don't add one drop at a time, it'll take forever, but just small portions, swirling to make sure there's no vigorous reaction ensuing before adding the next one. Just keep doing that until all of the hydrochloric acid has been added. You should be able to notice straight away signs that a reaction is taking place. The liquid will be going cloudy, and droplets of an immiscible substance will be appearing. The reaction takes a little while, so we'll need to leave the flask at this point for about a quarter of an hour to try and ensure as high a yield as possible. The next step in the process is going to involve a piece of apparatus known as a separating funnel. This is shown here in a clamp stand. You use these if you have immiscible liquid. So in this case, our product, the liquid, won't mix with the liquid reaction mixture. So we'll see two layers. With these separating funnels, before you put any liquid in, the key thing is to make sure the tap is closed. And most of the separating funnels have a screw-in tap, which you wind in until the white plastic cylinder is pushed up, blocking the hole at the bottom of the separating funnel. Don't turn it too tight, but turn it so that it's a snug fit. There is another type of separating funnel, and that has the sort of more classic burette tap with the handle that you turn. When it's in the vertical position, it's open. To close it, turn it to a horizontal position, and that prevents the liquid running out. So always make sure that you have the tap shut before you put any liquid in if you don't want to lose it. And it's definitely best to fill the separating funnel clamped as shown, so that if you spill any, it doesn't run down over your hands. Do put a beaker underneath it when you're filling it to catch any spills. After the 15 or 20 minutes reaction time are up, you can take your conical flask over to the clamp separating funnel and transfer in the reaction mixture. To help do this without any spillages, do use a glass funnel, place that in the top of the separating funnel, and then just pour your mixture cautiously in. Of course, the separating funnel tap is closed. We've already talked about that. Once in the separating funnel, if you watch carefully, it doesn't show too well on the video, you'll see two clear, distinct layers forming. The top one will probably be relatively clear, and the lower layer will be somewhat cloudy. In every case, with a mixture in a separating funnel, whatever liquid is more dense will be the lower layer, and whichever one is less dense will be the upper layer. In this case, the reaction mixture that we're trying to dispose of, the excess hydrochloric acid, will be the lower layer, and our desired product, the 2-chloro-2-methyl-propane, is going to be the top layer. So we'll be keeping the top layer and disposing of the lower layer. So once you're satisfied the two layers have separated out, the lower waste layer can be run off into a container. It's probably best to use a beaker with a nice wide mouth to make sure you catch the liquid. Don't open the tap too much, otherwise you might suddenly find the liquid all running out and you losing some of your product. So just let it run out cautiously, watching the interface between the two layers, the point at which they meet, slowly creep down in the separating funnel. And as it enters the sort of conical shaped bit, you can slow down further and watch it very carefully as it approaches. So if you slow down to a sort of drop by drop, you can just close the tap as the layer between the two liquids reaches the tap. You've now got your product in the separating funnel, and at this point we've carried out a crude separation. The rest of the reaction mixture is now in the beaker, our product's in the separating funnel, but unfortunately we can't think of it as a pure product at this point. There'll still be contamination from traces of the reactants, for instance excess hydrochloric acid and unreacted propan-2-ol, as well as traces of water in the product, and so we'll need to remove those at this point. So the first thing we're going to do is a washing step, and because we're going to be trying to remove acidic impurities in this step, the hydrochloric acid, we're going to wash with a solution of a weak alkali, in this case 5% sodium hydrogen carbonate solution. That'll neutralize the acid and help it dissolve into the aqueous layer that we're adding. So we're adding about 10 centimeters cubed, only approximately measured, in a measuring cylinder of the sodium hydrogen carbonate solution. The accuracy is not important at this stage. You'll see that it doesn't mix with the product layer, it forms a separate layer, so we're going to need to do a little bit of mixing here at this point, and we'll have to be cautious because the reaction between the sodium hydrogen carbonate and the acidic impurities generates carbon dioxide gas. So have a look at the technique here, placing a stopper in the top, holding it firmly on, tipping upside down, releasing the stopper to allow the gas to escape, and then shaking a little bit more vigorously as the amount of gas evolved goes down. So do hold the stopper firmly on when inverting the separating funnel and tip upside down, always checking carefully, releasing the stopper to let any gas out so you don't get a build-up of pressure. Once it appears there's no more gas being evolved, we can allow the two layers to settle once again. As before, our product is the top layer and the sodium hydrogen carbonate solution is the lower layer, as that is more dense. So we can drain off the lower layer into our waste beaker again. We can expect to see some fizzing as that happens in the beaker, which will have hydrochloric acid in it. And so just the same process as before, allowing the interface between the two layers to creep down towards the tap. The washing process can then be repeated once or twice more until it's clear that no more gas is being evolved. We can then do a final washing of our product with distilled water. So again, approximate 10 centimeters cubed of distilled water added to the separating funnel, and this just helps to wash out any further water-soluble impurities from our product. Stop of the flask again, the separating funnel again, release the pressure, if not much should form this time, but still just to be safe a few times before leaving the layers to settle. We'll show you at this point one common mistake people make, which is to leave the stopper in the top of the separating funnel. If you do that, when you go to drain out the lower layer, you'll find something surprising happens. A few drops come out initially, and then nothing seems to happen. And at this point you'll be under the impression that your tap isn't working. In fact, of course, with the stopper in the top, no air can get in, and so the liquid can't come out. So if you find that happens, if you realise nothing's coming out, close the tap again, remove the stopper, and now you'll be able to drain out that lower layer without any problem. So we've done some of the work now of purifying our product, but you'll see it's cloudy probably at this point, and that's because there's traces of water contaminating it from those washings. So we need to do a strange thing. We need to dry it, which sounds like an odd idea, drying a liquid. We'll see how it's done. We're going to transfer the product into a small 50 centimeter cubed conical flask for this purpose. So we'll lower the separating funnel down so that we're going to be confident of catching all our product, and we can just drain the product into the small 50 centimeter cubed conical flask. So just open the tap to let the crude product drain in. The drying process involves adding something called a drying agent, and the one that you're expected to know is anhydrous sodium sulfate. So it's an ionic compound, solid at room temperature, and it has the ability to absorb water. We can be quite generous with this, so transferring into the conical flask a few fairly generous spatulafuls of the anhydrous sodium sulfate. Once you've added a few, you can give the flask a little swirl, and what you should notice is that the anhydrous sodium sulfate, a lot of it will kind of clump together and stick to the bottom of the flask. You'll also notice the liquid getting bright and clear. And to be assured that your product is dry, you just need to keep on adding the anhydrous sodium sulfate until your liquid is fully clear, and there's some free anhydrous sodium sulfate able to swirl around the bottom of the flask. Once we're confident that the drying agent has absorbed all the water from the product, so the product is looking nice and clear, we can go ahead and see how much we've obtained, what the yield is. To do that, we're going to put the product into a sample bottle. We're going to weigh by difference. So set the balance to 0, put the sample bottle on the balance and record the mass. In this case it's 17.26 grams. And then we can carefully decant our product into the sample bottle, just leaving behind the drying agent in the flask. That's fairly easy to do. 17.26 empty, we'll weigh it again, 28.79 with the product in, and so if we subtract the 17.26 from the 28.79, we can see the yield of our product. Now, there's still the possibility our product isn't entirely pure, so a further process we could do would be distillation. In distillation, the impure product is placed into a glass flask. In this case, it's a round-bottomed flask because it's got a round bottom. There's also a flask called pear-shaped flasks, which come down to a bit more of a point at the base. As well as the liquid, you'll add some little granules called anti-bumping granules. This is an inert material that just provides a surface for bubbles to form during the boiling and makes the boiling process smoother and less likely to splash material up out of the flask. The heating is provided by a device known as an electric heating mantle, and this works without a naked flame, so in terms of flammable materials it's much safer, and it also has a much greater degree of controllability for the heating process, so a much gentler heat than can be provided than would be provided with a Bunsen burner. The flask is lowered into the electric heating mantle. An adapter is fitted to the top of the flask, shown here. It's got a side arm coming out of it, and when the liquid boils, the vapours that are produced will travel up out of the flask and down this side arm. The top of the adapter has a fitting to allow a thermometer to be placed there, and that'll tell you the temperature of the vapour that you're collecting, and hence the boiling point of the substance. This will allow you to be confident that you're collecting the correct substance, because if you know the boiling point, you can just match it to the temperature on the thermometer when a liquid's being collected. To the side arm of the adapter we fit a condenser, as shown here. This is a device used to turn vapours back into liquids. It has an inner tube passing right through it from the adapter, and then there's a wider outer tube sealed at both ends that water can flow through, creating a cool jacket. Whenever you use a condenser, you always attach the pipe from the lower end of the condenser to the tap, and then the pipe from the higher end of the condenser goes into the sink. That way, as the water travels into the condenser, it pushes out any air that would otherwise prevent the condenser from working fully efficiently. When the tap is turned on, a flow of water will pass through the condenser. You can just see it entering there, and you want to achieve a generous but not too powerful flow. At the far end of the condenser, a receiver adapter is placed, which just takes the condensed liquid down to drop it into some kind of collection vessel that can be placed under the end. So just to recap, the liquid in the flask here will be heated and boiled. When it reaches the boiling point of whatever liquid present has the lowest boiling point, that'll vaporize, turn into a vapor, and travel up into the condenser. We can read the temperature of the vapor to check the boiling point of the liquid we're collecting. The vapor will pass into the condenser, where the water-cooled jacket will turn it back into a liquid, and it'll travel down and be collected in the little collection vessel at the end. All that remains then is to turn on the heater, initially to a fairly high heat, and wait for the mixture in the flask to start boiling. When you're carrying out distillation, you'll always stay with the equipment, watching it carefully, adjusting the intensity of the heating to ensure a nice smooth boil, and watching the thermometer in order to check the boiling point of the liquid being collected. In general, you'll have more than one vessel ready to receive the liquids so that if something boils off at a temperature below the product you want to collect, you can collect that first and then move it out of the way as the temperature starts to rise again, and put another vessel underneath the end of the condenser there, and just keep on doing that until the liquid that you're intending to collect starts coming across at its boiling point. You also need to keep a very close eye on the contents of the flask, because you should never allow the flask to boil completely dry and carry on heating. That could lead potentially to a fire. So our flask is boiling now, and if you watch carefully, hopefully you can see drops falling from the condenser into the collecting bottle there. The temperature on the thermometer is reading 48 degrees. So if the product that we were intending to make in our synthesis has a boiling point of 48 degrees, we'll obviously be delighted that we've been successful on this occasion. Of course, the boiling point alone is not an absolute identification test, because more than one substance will have the same boiling point. So we'd probably carry on and do some further form of analysis like infrared spectroscopy or a chromatography technique.